Hello everyone, it's Professor Sabatini here at Passaic County Community College again, and today we are going to do lab number 3, experiment 9, calorimetry for the CH103 class. Chemical and physical changes in chemistry often involve changes in energy, and heat, a form of energy, is often released or absorbed during one of these chemical or physical changes, and the heat will always flow from the object of a higher temperature to the object with a lower temperature. The heat flow is going to be measured by a calorimeter. Today our calorimeter is 2 coffee cups, styrofoam coffee cups, nested together there. The styrofoam has a high degree of insulation, and the insulation prevents the heat from being lost to the outside surroundings. So any heat being transferred is contained inside the calorimeter there and will give us much more accurate results. Another property we have to consider here is specific heat. Specific heat is an intensive property, physical property of a substance. Intensive meaning it is independent of the amount of the substance that you have. Today we will be using water, and the specific heat of water is 1 calorie per gram degree Celsius. Doesn't matter how much water you have, it's always going to be the same specific heat. The specific heat is the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. As I said, waters is 1. Something like iron or metals have a much lower specific heat. Iron in particular is 0.11 calories per gram degree Celsius. So compared to metals, water is really good at absorbing heat. It takes a lot of heat to raise the temperature of water by 1 degree as given by its specific heat, which is also why it takes forever for water to boil, right? You have to add a lot of heat to change the temperature of water. Whereas the pots or pans that you'd be heating the water in, they heat up and cool down really quickly because they have low specific heat. Metals have low specific heat. So that's kind of what the specific heat means in real world terms. A calorie, I mentioned that the specific heat is of water is 1 calorie per gram degree Celsius. A calorie is a unit of energy. So that's all we need to know. It's a unit of energy. Similar to the food calorie, right? A food calorie is actually a measurement of energy. It actually is a kilocalorie, but we just say calorie with a capital C instead, so we don't have to say kilo, because people like to keep it simple, right? So in today's experiment, we're going to find the heat capacity of this calorimeter system that we built here. All right, the heat capacity is the amount of heat required to raise the temperature of some material by a certain degree Celsius, by 1 degree Celsius, right? So heat capacity is also used for objects like we have here with the calorimeter, right? The heat capacity is an extensive property because it matters how big your object is or how much material you have, right? You're talking about a specific thing rather than a substance in general. All right, so the heat capacity of the calorimeter will tell us how much heat gets absorbed by the calorimeter and will further refine our results. Now today we are just going to measure the heat capacity of this calorimeter, okay? And to do that, I've added 50 milliliters of cold water in here. You'll just have to take my word for it. I've also put 50 milliliters of water in a beaker here that I'm going to heat up on this hot plate. All right. The way that this is going to work is I'm going to take my cold water in my calorimeter, put the lid on there and the thermometer, and mix it up, and I'm going to monitor its temperature over 5 minutes. Now, not much should happen here, but we want the calorimeter and the water to be at roughly the same temperature. So I'm going to read the temperature right now to the nearest 0.2 degrees Celsius. So I'm going to estimate in there. My thermometer goes per degree. So it is right near 24. So I'm going to say it's 23.8 degrees Celsius. So I'm going to write that down at time 0. And I'm going to set a timer here. And I'm going to just watch every minute now for 5 minutes what the temperature of this is. It should not change much while my hot water here is heating up. Alright, so what we're going to do is we're going to find the baseline temperature of this cold water, and then we're going to, after 5 minutes, add the hot water to the cold water. And then we're going to measure the temperature change of the cold water and the hot water. The temperature change can be used to then calculate the amount of heat lost by the hot water and the amount of heat gained by both the cold water, and the calorimeter is going to absorb some of that heat too. And we're going to need that heat to determine the heat capacity of the calorimeter. How much heat did it absorb? Since heat is a form of energy, energy cannot be created or destroyed. So any heat that's lost by the hot water will be gained by the cold water and the calorimeter. And some small amount will be absorbed by the calorimeter, and we can use the magic of science and math to determine that, which we'll go over in the calculations part. Right now, though, we're just going to do the lab. All right, so I hit another minute here, and now I'm going to say this is 24.0. Heat it up a little. It's a little warm today, so it's a little warm in the lab. I don't anticipate it changing very much from there. All right, I'm going to go grab another thermometer for my hot water, and I will be right back. Just to keep an eye on it. Right, we hit the 2-minute mark there, still 24. In order to determine the actual final temperature after we mix these two together, you're going to have to make a graph. And the graph is going to have your temperature of your cold water, and then when we mix it, it's going to spike up, obviously, when we add the hot water. Right? Once I add the hot water after 5 minutes, I'm going to record the temperature every 30 seconds for 5 more minutes. And that'll give us a graph. Then you're going to have to extrapolate the data from that graph, because all the heat does not get transferred at once. It takes a little bit of time there once it mixes up. So again, that will be done in the calculations portion there. But we will be making a graph and monitoring, using the graph to determine the actual final temperature. The change in temperature is always the final temperature minus the initial temperature. All right. So when something gains heat, excuse me, my 3-minute mark is here, and I don't think our temperature is going anywhere. When something gains heat, the final temperature is higher than the initial temperature, so your change in temperature is a positive value. When something loses heat, the final temperature is lower than the initial temperature, so you get a negative value, which represents it losing heat. Negative would be losing heat. All right, our hot water is almost all set here, and my cold water is just going to hang out for 1 more minute. So I'll take another reading. Pretty sure it's going to be, 24.0. So we got 1 more minute. This is almost up to 70, which is what I wanted to see. Perfect timing. And then we will mix them together and record the data there. You can use calorimeters to measure any type of energy change, and that's also how you would measure the energy in a food, right? You basically blow up the food in a bomb calorimeter, and then you measure the temperature change, and it tells you how much energy is in that specific food. Oops. Right, 15 more seconds. Okay, I'm going to go with 24.0. All right, I'm going to allow this here. I'm going to take the beaker off and just allow it to kind of like settle down here so I can get a accurate temperature reading on it. I need the temperature reading of the hot water initially as well, right before I add it, so that I can find the change. Alright, and I'm going to go with 65.4. That's the initial temperature of my hot water. Now, take this thermometer out, pour this in here, mix it, and record the temperature once I get there. Right, I got 58.8. And then another 30 seconds, take another reading. Give it a nice mix up there. And now it started going down, 58.6. Actually 58.0. Right, 55.4. At the 7-minute-ish mark right now. 52.2. 51.4. 49.6. 47.8. 47 even. 2 more. 45.8. And the last one, 44.6. All right, so for the initial temperature of the cold water, we had 24.0. Initial temperature of the hot water, 65.4. And then, again, T-final is determined by a graph. It is not the first temperature. The first temperature that I recorded, the highest temperature was 58.8. That is not T-final. You determine it by a graph, right? It's explained in the lab manual. It will be explained on another video. But then we ran all the way through, went from 58.8 down to 44.6. But you're going to use that graph to determine your T-final. So thanks for joining me today, and I'll see you again in the next lab.